The first one being by Stephan Eckes, who is an audio and AI engineer based in Berlin. So without further ado, let's give him a massive hand. Thank you. Yeah, thank you. Super cool to be here. It's very nice to contribute to Rust Nation as well. It's been a nice conference. Been here last year already, and yeah, I want to talk to you today about deploying AI models or machine learning models in general with Rust, and the whole landscape that we already have. And yeah, just a little bit about me. I am, or let's go through the talk. So first I will talk 5 minutes about me and my job, how we started with the company. Then I will give you an overview over the AI landscape in general. So which model types are there, which inference engines are there, what you can use for training and for inference. I will show you the Rust ML frameworks that are available already now. We'll go a bit deeper into the Rust inference engines. So how are they powered? How can you build your own if you need something special? And finally, verdicts, making sure. So yeah, about me. I am a hobby musician, so let's sing, piano, synth, DJing. That was all my life. But I also was always into programming, so I started to study computer science, but later went into audio research because it's just a very interesting field, how our brain works, how we perceive sounds, and also there a lot of programming was possible. So doing room analysis, programming synthesizers, and so on. That was what excited me in life. And I always did a little bit of open source work. So, for example, if you check out the project Artisan Standalone, that's what I did after meeting some people from LLVM. They were doing the real-time sanitizer. That was inspired from LLVM from last year. And yeah, we try to make this available from Rust. So with that, you can check if your code uses any allocation or calls any function from Linksy, then it will make sure you exactly available with one of these functions. And this is super useful for audio, but also for buttons and everything, real-time guarantees. And as the new DSP, I try to work a bit in public and show how to call audio devices and build frameworks around audio processing. And then as in my professional career, I worked for a bunch of audio companies in Berlin. So you might know Neumann, the microphone company, UHE for Berlin Synth. With Holoplot, we were building the sound system for the Sphere in Las Vegas. It's a huge sound system, maybe the largest one on the planet right now. And yeah, with a startup in Berlin, we were building the whole system. And that was the company where I learned Rust, actually. So super grateful about that. We had every Tuesday, we had Rust learning sessions in the company, which was awesome. And then I joined AI Acoustics. AI Acoustics is the company of a bunch of friends of mine from uni. So they were audio researchers as well and wanted to build a reliability layer for voice AI. So when you try to talk to ChatGPT or you have conversations with agents, you might notice that often the AI model gets interrupted because of noise in the background or backgrounds. So we were focusing on building smart filter algorithms, AI models that can filter out the noise of speech and also make it smooth when near do completely proprietary voice recording. So we have a studio where we learn tourists and all the language to report it on the speech. We have a data set that has to release open source data set as well. And we can provide general training, so everything from scratch. And our complete SDK, so how we deliver this to other developers. And our real-time inference engine is completely written in Rust by now. So just that you know how that looks for the AI models, or it's on the left you see noisy speech, and on the right you see the clean speech. That is a spectrogram. So on the x-axis you have the time, and on the y-axis you have the frequency. And then you see beautifully here with like this area was obviously with the voice. So the AI model can learn this and then section. We can only remove this if we also equalize the voice to make sound or make it podcast and the reverb of the room, and also we will fill our frequencies that on this. But that's how it is. By those miles. And then for like those AI models, you have word error rate, but on speech to text models, so how many words are wrong from a transcription. And then you see, for example, here, this is a data set. The gray bar is for the clean audio. So that was recorded by the phone. And then the blue one is when we use our model in front of it. So we just have way less errors for the transcription. And now we are integrated into LiveKit, for example. We are now their first party plugin that you can just enable. LiveKit is used for a lot of audio pipelines on the computer, video pipelines. So we have another talk today here for a video chat app, or it's like a screen sharing app. They also use LiveKit for this. Pipecats is another framework that you can build AI agents with. We integrated as well. And even stuff like Elgato, I don't know if you know the Stream Decks. They build microphones and webcams as well. And they use us as the technology for the instruments. And now there's the case quite a complex product now. So we have Airtem, which is an inference engine. Before SDK, which has elements and one best. And or the something with around it, and this is already from us with private, and then everything from you is public. So we have bindings, we have the resin SDK, and from binding we should have a language. Might wonder why we not build Python directly from here. I could change this in the future maybe, but now it was just nice to have the bindings, to have a defined interface that is well tested, and to have more stuff in public. So we can just send out another compiled library with the C bindings, and then clients can build this themselves and switch this out. So it's a bit more flexible. But I also see upsides of going directly from here to Python. So yeah, it's just interesting when you're responsible to come up with all those solutions. In fact, that's very interesting. And what I learned is really once you publish a public Rust library, or once you publish a Rust library that contains another Rust library, which is private, it actually doesn't work statically. So then the simply slash. And I never heard of this. I guess Rust is on an open source project, so I know we have this issue. But then you need to many webs use LLVM or so to hide the symbols, and it feels a little bit scary to do it, but it works. And dynamic linking works. Yeah, just about the journey. So 2023, I was joining AI Acoustics, and the problem of them was they had great Python models for speech enhancement, but they didn't know how to ship this to clients. So they were all Python developers, and the clients needed to integrate this into a real-time system. They needed fast and small compiled libraries. And yeah, they didn't have this deployment experience. So that's where I joined the company. And then I got the models of them and had to find a solution how to bring this to the client. So I tried basically most inference engines out there, to see what works, what is the fastest way to do it, which loads our model and all. So I want to walk you a bit through what is actually available on the landscape and what I learned. So first, to clear this a bit up, there are frameworks that are mostly for training, and there are frameworks for inference. So for training, we're most common with PyTorch, right, from Meta. Most researchers are using this. TensorFlow, the siblings it's getting a bit smaller now, so less people are using TensorFlow all the time, but used to use it a lot. We came up in with Jax, and I using Jax as well. And now Pedal is kind of this newer framework from China, from Hollywood. And most of those Chinese models are trained with Pedal. And then you have inference engines. So there is stuff like Llama CPP, Onyx Runtime, Light RT, which they just rebranded. It was formerly TF Light, TensorFlow Light. Executorch is our new approach of Meta to bring this into their framework. So, because PyTorch models, exactly, you have this problem how to deliver the models. So with Executorch, they want to tackle that. And TVN from abstraction, they try to NLVM for machine learning. So that's why it's about the VM thing, which should be. But TVM, yeah, wants to the voice compiler. So they just give the model architecture by the platform. But it's all so early that it's like the advertisement is so promising that then you test it and it's super hard to build. And then it's super slow or it doesn't work with the model at all because it's so early. So yeah, it's not, the landscape is just so, everything feels like an alpha. Why are there different frameworks? So for training, you have to focus on flexibility. You want to have all the features available because researchers want to test everything and try things out. It's actually enough if it runs fine on GPUs because the training has to be done on GPUs anyways if you want to be fast. And at least its interface mostly for Python because, yeah, researchers just are used to Python. And the inference side needs to focus on speed and size. It needs to be compiled into apps and devices. It needs to be cross-platform, right? You want to do inference on a microcontroller. You want to do it on a server, on a GPU, and everywhere around. So on phones and everywhere. And that's why most of them are in C++ and are also interfaced from C++. So that's just the ecosystem I went into. And so because back then I didn't find a lot of projects that were very fast. I also started to C++ and built some prototypes so can deliver this with clients. But then it got even more complicated because you have those inference engines like that I showed you before, like Executorch and LM. But then they have 100 different languages. So basically, every vendor, every chip maker has their own inference framework. So that's really complicated. Everyone supports different layers, supports different quantizations. Yeah, it's not an easy world to be in. So you have ARM-NN specifically for ARM microcontrollers. You have Apple Core ML for the Apple M chips. You have Intel OpenVINO for those Intel NPUs and GPUs. You have Qualcomm QNN for mostly those Qualcomm processors, Android and NAPI, and it goes on and on and on, right? Yeah, so I had to dig through this because we always had clients that said, we would like to integrate it in smart glasses, or we would like to integrate it on an iPhone. So I always try to find a fastest solution for this with a big client. It's definitely complicated. That's not quite why we get started. And then on top, we have all those model formats. So we find models in 100 different formats where they are stored. The most common ones are Onyx, Safe Tensors, GGUF, .pt. Those are the PyTorch weights how you export it. And some of them are completely standalone. That means they contain the graph and the weights. So just for this file, you can run the inference. And some of them are not standalone. That just means they contain only the weights or only the weights and some metadata. And then you also need the model code. So basically it just contains the data, but the code needs to be built by yourself to run this inference in the end. So you need to find someone that already implemented it. And GGUF is one of the most common ones for large language models. So if you search for like Gemma 3 open the weights, or so we often find GGUF models because GGUF has one of the best quantization supports. They support even key 2, quantization 2. That means you have every weight quantize it down to 2 bits, which is super small. Also, wir wollen sagen, was ist Marketing jetzt with words, but in force for LLMs quite well. And it has very fast loading times. but it's also not fully standalone. So it needs to be implemented in the inference engine. So here it's likely published to Llama CVP or GTML. This is open source ecosystem from Georgi Draganov. And yeah, but also some other inference engines are supporting this TTO format now. And then one of the most prominent is Onyx, because it's really diverse. It's for all model types. It was developed by Microsoft, and it's a fully standalone format. So you really have the graph and the weights in one file, which is super cool. And nearly every framework supports Onyx. So it can either convert from an Onyx file to the framework native file, or you can directly load the Onyx file. So it's the most diverse model format. But the downsides of this are the loading times are smaller because it contains way more information. To rebuild the graph at runtime, some bits in load the file, and then you basically have the dynamic graphs. And with the other frameworks, often you have it full static because it's already that's right. So that's why sometimes it can be slower, but also some frameworks do this differently because they just convert from an Onyx file to a model, to the framework native format, and then the slow and they don't have it. And this is how an Onyx graph looks, for example. It's now this is a very simple model, MNIST. Some models get really large, but this just contains the full graph from the input to the output, and then every operation that is in between, and also the structure. So sometimes you have more difficult things like here, branches that go from there to there. So yeah, it just contains the full information. And this is how you can view Onyx models. That is Netron. It's a nice open source application that you can run in the browser to analyze model files. And then safe tensors are the last I want to talk about, because safe tensors are used everywhere now. It's from Hugging Face and actually written in Rust. The model format, or the code how you can generate those safe tensors. And it's just data, so it doesn't contain the graph, it's just the weights. But the upside of this, there's also no code injection possible, because it's really just plain data. And you have zero complete deserialization through the Rust framework, very fast moving. So now it's kind of becoming again stuff with insertion. But you need to know where the safe does on this. You cannot just run right and still need so and then all those changes with formats. So Apple ONA has their own format. VDR Tensor actually has their own format, and so on and so on. So if you find these, they will run just with a specific framework. Now the new one here, Executorch, started their own one that is PTE. Also true, because the .pt also only contains weights, and .pte is now completely standalone because it's for this Executorch framework. Yeah, so how do you evaluate which inference engine you can use? If you have a model that you want to run, you need to check what is the model format. So if you already have it, can you convert it to another format that you want to use? The operator supports, does the engine actually support all the layers you need? Quantization, do you need quantization in your model? Does your engine support quantization, or even some, for example, if you want to run it like engine use, like new web processing units that are in the newest generations you can use now, or system driven, then sometimes you can only run it with quantization, so they cannot inference with floated. So that's what you have to figure out, what you have there. And then the target platform, obviously, where do you need to run? Do you need to run MapC on a GPU, whatever? So then maybe another framework is better for you, depending on where you need to run. And lastly, performance. There are just some frameworks that are not that fast, but they're nice and flexible. So is performance a bottleneck for you? Do you need the fastest performance or not? And depending on that, you can choose a bit which inference engine is right for you. And then I had the question, okay, I tried everything and I found out it's super complicated. The build process is super complicated. Often it's crazy complicated libraries with Python build scripts and somewhere see make and then Bazel as a build system on top. And it's just, yeah, it was super hard to build it for a specific architecture with a specific backend. So I thought it would be so nice to have something in Rust where you just do cargo add and it runs. Can we do that? Is there a possibility? So I dived into that and looked, are there already frameworks available? And yeah, so I wanted to use it obviously because everything that makes Rust great elsewhere applies to ML as well. You have the cross compilation, which just works really nice for different architectures. You have the memory safety, you have the great optimization, even for different targets, and the awesome tooling. But the risk was, I mean, I tried to bring this then to my colleagues and say, hey, it would be so nice if we can work on this a bit, because I think it would be awesome if it would work. But the risk was that it was not really a proven path that we found. C++ is just the industry standard. What if we can't find the right tools? What if it's too slow? Also, what if it's a problem for our clients? Like recently, we just had the problem that a computer game wanted to integrate us for real-time conversation, but then they need to run on PlayStation, and there's no Rust for PlayStation possible at the moment. Stuff like this, right? It's just a bit of a risk. But we bet on Rust anyway, and said I could convince them. And that's the nice thing when you join like a really young company, that you can then have a bit more influence. Yeah. And now I want to walk you through the Rust ML frameworks that I found and what they are able to do by now. And one of the most diverse frameworks that you can use is Ort. It's really nice, but it still has a C++ backend. That's why it's just a wrapper around Onyx runtime. But I mean, it's an upside and a downside. Because the upside is that it's really mature, right? It can run any Onyx model you find. Everything just works, and it's super fast. And the cool thing is, even though it's just a wrapper around the C++ framework, it's much easier to use than the C++ framework, because they build really nice tools around it, and they have static linking of precompiled binaries for a lot of different targets. You might not want to use precompiled binaries, but you can, and this just speeds you up a lot in testing, right? Or in just trying things out. Is it something, can it run my model? Is it something I want to use? And you have access to all execution providers. So execution providers are those vendor-specific backends that you can choose. And they even now try to integrate Rust backends. So Candle and Tractor are other Rust inference engines, and you can use them through Ort. So it's interesting where this is going. And supported platforms, because it's still the C++ library underneath, so you cannot just compile it everywhere where Rust compiles. But yeah, you see all the major operating systems are supported, even web now. And all the red ones, the one in bold, they are available as precompiled binaries. So you really just do cargo add and it works. That's awesome. And the execution providers that are supported are those, so you can run it nearly everywhere. So Apple CoreML is also there as precompiled binary. Windows DirectML is specifically for Windows, but it runs on any hardware. And here are the ones for the different CPUs or GPUs. So here's NVIDIA, you have Tensor RT and CUDA. For AMD GPUs, you have MyGraphX, not yet available as precompiled library, but then you have to compile it yourself. And WebGPU or WebNN is available. And yeah, if you see that you have always stuff like CUDA and TensorRT, or WebGPU and WebNN. What is the difference there? It's just TensorRT and WebNN, they are layer higher, so they already implement complete operations for machine learning models. And WebGPU or CUDA are just more generic compute frameworks. So sometimes it can be faster to run the model in WebNN or TensorRT, but they have less support for less common operations. So sometimes it only works with CUDA or WebGPU. It's just the thing. And yeah, I think the precompiled binaries matter, or at least it mattered for me a lot, because I don't know if the execution provider is faster for my model. Sometimes it's not. And if I can just do cargo add and change the feature flag, and then I can at least immediately test, does it run faster? Is it something useful? Because building it yourself on on building Onyx runtime yourself, it needs a lot of dependencies, and it can be super annoying, especially if you need those frameworks from the hardware vendors. And yeah, I just needed a lot of time to test it, and then I found out, oh wow, it's not faster to use XNNPAC, it was just faster to run Onyx runtime in default mode. That depends just on your model and the architecture, so you cannot find this out otherwise. You cannot just search in the internet if it will be faster. And by default, Onyx runtime only builds dynamic libs. So for static libs, you have to follow community projects, you have to customize the build scripts a bit, you have to find all the dependencies that are necessary to build a static library. And with ORT, the framework in Rust, it's just static by default. You can still use it dynamic, but it's static by default, and that just makes app delivery so much easier. I mean, in Rust, we do most of the things static, right? Ups and downs there as well. But yeah, the precompiled binaries just give you the fastest way for testing multiple backends. If you don't trust it, you can still build it yourself, right? And if you want to see how that works, so you just do cargo add ort. They are the version 2 is in a release candidate, but it's stable. It's just because the API might still change. So they want to release the 2 version in a couple of weeks already. And then you add the execution provider you want to use as a feature here. If you don't do that, you will just use Onyx runtime in default mode for the CPU, but this is also super fast. And then for the setup, you just have the session builder with a Rust builder pattern. You can then choose which execution providers you want to register. So you can even put here QDAR, ROCm. You can use all the execution providers you want to use, and then at runtime it's figuring out if that's available or not, and chooses the execution provider that fits best. So also in the order you put them, it will try to use them, and then ends probably in the default CPU when it cannot find the GPU drivers or so. And then with the commit from file function, it will generate the model graph, right? So as always, that takes a second because it has to build the whole model graph at runtime out of the model. And then for the inference, it's very easy. It has support for ND array. If you don't know ND array, it's basically the #1 framework for matrix operations in Rust. So it's really nice to have this included. And you can generate an ORT tensor out of it, and then just do model run with named inputs even. So you can find out the input names in the model graph, analyzing it with, how was it called, Netron, the app. And then you get the output. So it's as easy as this, and you can run the full inference. There are downsides as well. I mean, it's still a large C++ dependency that can cause build problems or linker errors that you have to debug. For example, we are shipping a library to other clients again, and then sometimes building again a C interface for that, there were just build errors or linker errors, and we had to find out how this works. So it's not as easy as having just Rust. And so you still need manual Onyx runtime compilation for some platforms or execution providers. And especially the pre-built libs, they need rather new OSs. So you need Windows 11, macOS 13.4, or Linux 2.39. And this is rather new. So we had a lot of clients asking for older Linux versions, and then I just couldn't deliver it immediately. And you don't have a Vulkan execution provider. It might not matter for you, but Vulkan is, for example, the fastest option for consumer AMD GPUs. Now we have a look into Burn. That's a pure Rust framework. You might have seen it because Burn also does the people from Burn also give a lot of talks at those conferences here. Burn is actually training and inference in Rust. You can import weights from safe tensors, this format that I showed you, basically the default thing at Hugging Face, and the .pt format, which is from PyTorch. You have to program the model from scratch. As I said, like those safe tensor and PT formats, they don't contain the graph, so you have to find the code or program it yourself. But they also have a compile time Onyx import, which is nice, but it's still a bit limited. So I tried to load our more complicated model, and then there was a layer that wasn't implemented yet to convert, or when it converted, it had different outputs because it's not perfect yet. I mean, it's very complicated to build this graph, to build this from with an automatic mode. So programming the model from scratch might be faster because you can see what you can merge and so on, and more reliable. But they are working heavily on this Onyx import, so to make it more easy to use Burn. And you can run it on CPU, GPU, web, and even no standard, but it still needs alloc because it's using ND array as a backend for this. Yeah, we will go into this a bit later. So the supported backends are web GPU through WGPU, this nice GPU framework. This target also runs on most GPUs, so not only in the web. You have CUDA for NVIDIA GPUs, ROCm for AMD GPUs to running through HIP. HIP is basically the compiler for AMD GPUs. And the cool thing is that HIP even works on CUDA, which is kind of funny. So AMD wanted to make it to get into the market, so they made it compatible with CUDA as well. Then Metal for Apple GPUs. Vulkan support is nice. So as I said, Vulkan is the fastest for consumer AMD GPUs often. And CPU. And then it's just using the Rust compiler, right? With SIMD for most kernels and most CPU architectures. And for the Onyx import, you can find at this link, supported Onyx ops on the GitHub page, you can find the full list. So if you have an Onyx model that you want to run, you can check if all the layers are actually supported, and also the automatic import is supported. So you see some layers might have support in Burn, but not the import is not yet written. But the list gets really green now. So now only a couple of operators are not supported anymore, which is super cool and a really nice progress from the last year. You have already pre-trained models, available models that they implemented first party or other people implemented. So then you can just load the save tensor file and use the model. And you see there's already a nice list like Llama, Whisper, MobileNet. So you can see maybe the model you want to run is already implemented in the engine, which is pretty nice because it's a bunch of work to implement this model. And this is how you run it. So also there, just cargo add burn. You can select the backend with features. So here we're using CUDA. Fusion is just for kernel fusion. So it takes a bit longer to compile, but it tries to merge kernels into one if it's possible, which just speeds up the model a bit. Then you have the model struct, which is generic over the backend. So every layer basically that you choose here is also generic over the backend, so that it can run on GPU or CPU or microcontroller. Here we have two linear layers, one dropout layer and one GLU activation. So it's very much like in PyTorch. If you find PyTorch code, you can mostly translate it very nice to this framework. And then this is how you build a model yourself. So you have the forward function and just have an input tensor, which is also generic over the backend. And then you just put it to the graph manually. So you call every forward function, get the output of the layer, and then return it from the model forward function. Yeah. And then you use the model like this. So you choose your backend. Here we use CUDA. And then we create a model with the config. The input tensor can be built like this. And then we just run the inference. And the Onyx import works like this. So you have the build.rs script where you can use the model generator. You select your Onyx model file, and then it will just generate this code that we just seen automatically, right? Or tries to. So I said there still can be issues sometimes, but it works already for a lot of models. And then we can just include this generated file in our normal Rust code. So that is a super nice feature. Still, there are downsides. It is still slower than Llama, CPP, or ORT, but that again depends on your model. So every model can be a bit different because they focus on specific layers. But in general, everything I tried was still a bit slower. There's no NPU support yet. So NPUs are those between CPU and GPU. They are for smaller models that can speed up that a lot. That can speed up the models a lot while being energy efficient. So you have them in your phone and on the newer laptops. This is not supported yet, but they would like to support this in the future. You don't have quantization support, which is a big issue for large language models. But also that is something they want to work on. And yeah, the Onyx import is not yet perfect. And if you want to run on microcontrollers, you can, but with ND array, it's quite large and slow. So depending on your model size, it might not be the perfect choice. And if you have a small model that can run on a microcontroller, it might be better to just code it yourself. Then Candle, also super interesting, now from Hugging Face, but originally developed by Laurent from Qt. It's a great framework, also training and inference in pure Rust. You can import weights from safe tensors and PT, like in Burn, but additionally you can import those gguf files, which are often large language models are often in. You have quantization support, so it might be the better option for large language models, but you have to program the models from scratch every time. Though you have a nice selection of already implemented models, maybe you find the one you want to run, and the backends are also more limited. So you can only run on CPU, on CUDA, and web. So there's no AMD GPU support, no Intel GPU. It's not as generic. So Burn tries to be way more diverse in that sense. Available models, here's just a short list, so you can find more models here. But some of them are more interesting. So you even have Gemma, you have Star Coder, you have Stable Diffusion XL. So yeah, some of the interesting models are already implemented in that framework. And you add it like this. So you have Candle Core and Candle NN. And it looks exactly the same, right? You just do feature CUDA or feature web if you want to run it in the web. And here you have core and NN, because in core you find all the tensor operations and basic tensor stuff. And in NN you will find the layers, like in PyTorch, so conf2d, this stuff. And then it's very easy as well. Here you don't need to be generic over the backend. You just add the layers you want to run in the model. And in the forward function, it looks very similar, right? So everyone tries to be close to PyTorch. Here you just do forward this layer, then run this layer, then run this layer, and return the result. And for the to run the model, it also looks pretty similar. So we set up the layers with weights and biases. We set up the model. We load the tensor. Here's just random data. And we run the forward function. And this is how we do the inference. What is special here is we can select which GPU it should run on. So 0 just means the first GPU in the system. Downsides here, you don't have real Onyx import. There is a crate inside for Onyx import, but it's so alpha and it doesn't really support a lot of layers. So yeah, you can forget this at this point to make use of that. You don't have support for AMD GPU or cross-platform GPU like Vulkan. You don't have NPU support and also no standard. But if you want to run a large language model on CUDA, it might be a good choice for you. And then I'm a big fan of Tract. Tract is from Sonos. It was initially a startup from Paris that was just building this engine, and then they sold it to Sonos, and now they do, I think, this homomorphic encryption, so running machine learning models on completely private data and having the results private. Super interesting startup from Paris. They formerly did Tract. And this is also inference in pure Rust. You can import Onyx models, and most of them, so it just worked for all the models I tried. You have a great CLI tool to analyze the models and benchmark them, which is awesome because you don't know yet if the engine supports your model. So having a CLI tool where you can just do tracked my model and then see if it runs and how fast is amazing. It helped a lot, but it's CPU only. So it's really just for CPU. I think Sonos is using this for wake word detection and so on. That's why they bought the engine. And it's really fast. So it's well optimized for x86 and ARM64. For some models, it was even faster than Onyx Runtime, the big engine from Microsoft. This is how you add it. You choose tracked Onyx if you want to import Onyx models. And, oh, that was the wrong direction. And then just choose your Onyx path, your Onyx file. into optimized will then work a bit on the graph and try to speed things up. And into runnable then gives you the actual model that you can run the inference on. So here we have also support for ND array, and then you have this model run. Very easy, and it just works for a lot of models. All right, and the CLI tool, cargo install tracked, you can just run the CLI tool, and then you have this dump command. So here we check out MobileNet, the Onyx model, and with the dump command, you will see all the contained layers and the architecture in the terminal. With the criterion command, you can run the benchmark, and then we will see, cool, it worked, and we have an inference time of 43 milliseconds for MobileNet v2 on the CPU. And with the profile cost command, you can even see the distribution here, which layer takes up the most time. So here we see 60% of the time is on the deathwise conf. So then it would make sense to optimize this layer if you want to speed it up. Downsides, no GPU or NPU support, right? No standard support. I'm not entirely sure about the quantization support, though it supports most Onyx operators, and I think some of them are quantized. But yeah, you will have to check if you need quantization. And some Onyx operators are still missing, though it's really near complete. They also have a list directly on the main README of the supported Onyx operators. And then we even have a bunch of other inference frameworks. So R10 is quite interesting, has Onyx import for CPU and BASM. Microflow is very tiny, so you really just have a bunch of layers, but it was the best option by far to run on MCUs. I tested it and was running on a little daisy seed, and it was way faster than Burn on the microcontroller because it's made for this. But yeah, you only have, I don't know, 3 or 4 different layers that are supported. Then DFDX is kind of abandoned, but it's quite interesting as a project because you have compile time shape checks, and it was using a lot of also nightly Rust features for that to make it really nice from the usability. Runs on CPU and CUDA. OpenVino from Intel has official Rust bindings, which is super cool. So they maintain them. And then if you want to run on Intel hardware, even on NPUs, you can use OpenVino directly. And CoreML-RS is a young framework. But I mean, the bindings are still kind of experimental, but it works. And if you just want to run on Apple hardware, this might be something you want to look into. But yeah, at AI Acoustics, I basically tested all of them. I tried to run our models there, and still none of them were really perfect for us. Our requirements were real-time safety if possible. I mean, larger models you want to run in a background thread anyways, but our very small models, sometimes it can be nice to just run synchronous in the audio process because it's fast enough and it makes things easier, and we want to have the shortest latency. So if it's possible, it would be nice to have no allocations in our forward function. No standard would be nice because we can have a smaller binary size and we can run on any device. We don't know which clients are coming in the future and so on, so we just are less limited there. Another thing is, just to have precise control, like when we see, oh, we have this specific layer that is eating up most of the time, we could optimize it ourselves really fast. And yeah, we need to be very fast. But fast for our models, like specifically, right? And available frameworks were often too large, not fast enough, missing critical layers, some specific for audio. So for example, we also need STFT and ISTFT, which is made to build those audio spectrograms. And those are in PyTorch frameworks, but often not in the inference engines. And yeah, or they were requiring standard. So I was looking a bit inside of inference engines. So if you want to run on CPU, you can use ND array for n-dimensional arrays with dynamic shapes. It supports no standard as long as you bring an alloc. And you have multiple blast backends. Yeah, I will go a bit faster through this because of the time. But this is how you could build a layer directly with ND array. So you just have the weight and the bias and the sizes. Then set up the layer how you want to, and run the forward function. So you see it's quite easy. You just have the weight and then the matrix multiplication with the input, and then you just add the bias. And then you already have a linear layer, which is used a lot in machine learning. Then an algebra is also interesting. It's only for 2D matrices, but you have static shapes, and it's fully no standard compatible. So this is a better option for microcontrollers. And you have sparse matrix support, which is great. That means if you have matrices that have a lot of zeros, it will just skip them instead of compute them, and that can make things way faster. But if you want to have 4D matrices, you need some workarounds. And there it looks like this. So you have generic constants for the sizes, and then you can set up the matrix with constants here and set up the layer and run the forward function. So here it looks even simpler because we don't need any assertions or tests for the sizes or compile time checked. So we can just do weight times input, which runs here the matrix multiplication, and then add the bias. And then we have the linear layer with an algebra. But yeah, for 4D matrices, it's getting a bit complicated then because we need to build a wrapper basically and have an array with matrices, and in the matrix an array each, and then we have a 4D vector. But yeah, it's not perfect. And in general, for CPU acceleration, you can use GEM. GEM is a great framework from this homomorphic encryption startup that I told you about from Paris. It's the fastest matrix multiplication by far. It's really also I mean, it can compete with all the public C++ frameworks. MicroGem is nice for microcontrollers. You have BLAS bindings in Rust if you want to do specific linear algebra algorithms on CPU. CMSIS bindings are there as well if you want to run on Cortex-M, for example, and speed things up. Yeah. And then just to have a look in GPU, where Rust could get really beneficial for the future, actually. So GPU programming is super complex and feels like a step back to the 90s. That's what I read a lot of times, because you need those crazy shaders and things just work different. And then it's also complex because how do you choose now if you want to use CUDA, HIP, Vulkan, Metal, or OpenCL? What is best for you? And it's very hard to find portable, high-performance GPU code that just runs everywhere. And this is, I think, also generating this NVIDIA lock-in, because people then just stick to CUDA, and then they stick to it and rather buy super expensive NVIDIA hardware instead of going somewhere else, because it would be more expensive to build the code from scratch. But the Rust community is working to change that. So there are nice projects. And I think to have best generic GPU support in Rust could bring more hardware freedom. And this could mean Rust could be really a game changer for AI, because if it's very easy to compile Rust code for any GPU and it's fast, then people will use Rust because they are not that dependent on the GPU prices. There's a framework like Rust GPU. They say the future of GPU programming, so it's quite early, but they made it possible to compile the Rust standard library for GPUs and just Rust code. So you can write the GPU code directly in Rust. It compiles to Vulkan Spur V shaders. Vulkan runs on basically any GPU, as long as you're actually, I think Apple is wrong. I think Vulkan is just for Windows and Linux, but not 100% sure. And soon even the standard library will compile for that through host call. So with the host call framework, you can even run print lines and debug prints on the GPU. And to host call, it will then bring this to your CPU and print it out, which is awesome. And they also have the project Rust CUDA, but they are rebooting Rust CUDA at the moment, and they want to move it into Rust GPU. So then you can just target perfectly AMD, Intel, and NVIDIA GPUs, which would be a huge game changer. And the code looks like this. It's still a bit complicated, but it's Rust code. And you just need to write your kernel in Rust. And then here with this GID Y and X, you get at which process you are currently in the matrix. So here we run with 16 times 16 threads, in the X and Y axis, and then you can do heavy parallelization. Then there's WGPU. I think most of the people know it because it's used in a lot of UI frameworks right now. You need to write WGSL shaders, so they are not Rust. And it runs on Vulkan, Metal, and WebGPU. And it's used already by many frameworks. Even the Firefox WebGPU support is done by using WGPU. And also Bevy, ISD GUI, and so on. Cosmic Desktop, they all run their UI over WGPU. And the shader looks like this. So now it's a different language, but it still works. And here you see the kernel. And also here you get the GID Y and X, so where we are in the cube for our to run our kernel. kubecl is the backend of Burn. They are working on this to make like a nice compute language here. It's as well, you can program the GPU using Rust. That's more diverse because you can run on CUDA, ROCm, Metal, Vulkan, and the CPU. And yeah, as I said, Burn is using that as the backend. And this is how the code looks. So really clean. You just add the cube macro on top of your code. Then here you get this GID XY. You get it as a static number actually. And then you just write your kernel. So this is the simplest code we've seen, right? And others are, like I said, Rust CUDA, but probably moved into Rust GPU. And you have direct bindings to CUDA. This is a minimal wrapper around the CUDA toolkit, or ROCm. If you just want to target AMD hardware, you will get access to most of the ROCm stack here. But yeah, the biggest thing for Rust is, I guess, we're missing bindings for DSP and NPU accelerators. We had a lot of clients asking for example, for headphones. And on headphones, you cannot run on the CPU. It will use way too much battery. So they have DSPs inside, like the Hi-Fi chip from, how's the company called? I just forgot it. But it's, I think the current Intel CEO was at this company before. And those are incredibly fast in doing those matrix operations and energy efficient. But in Rust, there's just no way to access that because it's always, the vendor has to deliver the tool chains. And that's, we are working on this. Also, I see people that want to bring that in. Also, Fractile, where we meet tomorrow, they built now a stack in Rust to enable the running code on their TPUs that they're building. And in the end, we built our own inference engine. That is Air10, but it's not generic, so it's just for our models at the moment. But it worked nice. We power now the inference in LiveKit, Pipecat, Elgato. And I really just built really dumb Rust code from scratch. I didn't even do a lot of SIMD. I just used the auto-vectorization. Made a memory arena, so everything is now standard and no tensor is owning the data. And still, although I put so much effort into ergonomics and not make it really fast, we were in the end way faster than Onyx runtime. So you see, we were using 0.75 megabyte instead of 18, and ROM 6 megabyte instead of 30 in RAM, and 8 milliseconds worst case execution time instead of 16 with Onyx runtime. And I mean, I'm not a super intelligent coder. I was just like using this as my project and wrote Rust code, and it just was working so well. So yeah, that could also be an option for you. I think Rust can do AI everywhere. We can do server inference, desktop apps, mobile, web, embedded Linux. But as I said, DSPs and NPUs are still challenging. Sometimes we don't get the best-in-class performance. Quantization is still a topic. And bare metal MCUs are not that easy yet. But I think it could really change and make things way easier for the developers. So yeah, we just need more contributors, more success stories, and bring the vendors on board, right? That they also build APIs for their DSPs or NPUs. I think we proved that Rust can power production AI systems at scale. And I have to say, although it seemed like Rust could slow us down, in the end it enabled us to move faster, because if a client is asking, hey, can you compile for this platform? I just do cargo build this architecture, send it to them, and they are happy, and they release their product immediately with this build, and I don't even need to test it, which is insane. Yeah, so from research to production, we can go from Python to Rust, from tiny chips to server racks. Thank you.
All right. Thank you, Stephan. I think there's maybe time for 1 or 2 questions before the break. Right.
Hey, thank you for the great talk and a lot of framework covered. As someone who is trying to get into machine learning and thinking of buying a hardware after trying to run this, as many of us, on CPU, and it's horribly slow. Can you advise whether it is worth investing into something non-NVIDIA, or is it better to stick to NVIDIA and just keep it?
I want to say just go with a cheaper option. Just go with a cheap Intel GPU and do whatever you can run on there. But if you choose NVIDIA, unfortunately, it will be easier to test like the cool projects that are out there, right? So if you just find a generic, I don't know, music generator, sometimes it will only run on NVIDIA. But there are enough projects which run on AMD or Intel GPUs which use Vulkan. And I think we have so many projects, it's not bad to limit yourself a little bit sometimes. That's my approach. But I also have an AMD GPU at home. And I think it's, I can just run all the burn models and play around with it and train my own models on the GPU, and it works. But if you just want to be as fast as possible and just use everything out there, then an NVIDIA GPU will be the better choice at the moment.
All right. Maybe one more question there.
So I'm interested to hear more about your experience with cross-compiling Rust for a bunch of different architectures and platforms in general. Were there hidden stumbling blocks there where things just didn't quite work the same, or did it really all just work?
No, it really just worked. We even had people asking for ARM64 no standard because they are running on a mixing console or something, and they don't have an operating system because they split their CPU into one part running Android and one part running without an operating system to the audio stuff. And I was like, I don't know if that works. So I looked through the target list and I found, oh, there's ARC64 no unknown. So no standard, and I just compiled it and sent it them, and they released the product. So yeah, I was like, okay, I never would have done this in C++, but
All right, maybe one more question. Yeah, okay, David.
Hi, thanks for the talk. It was great.
Thank you.
Did you, in your travels through all the software that you've reviewed, did you encounter VLLM and SGLang, the Python inference libraries, and do you have any opinions on them at all?
No, I didn't test VLLM. You say it's directly from Python?
Yeah.
Yeah, we didn't really look into that because we wanted to hide our models, right? So I didn't look into options where we need to expose a bunch of stuff.
Okay,
but I know maybe you don't need to expose something because you just load the model from Python and run it, but I'm not sure how that works. Okay. So unfortunately, no experience there.
I've got one more. What makes one of these inference libraries accessible from a developer's point of view? What drew you to a library? What pushed you away from a library?
The biggest thing that pushed me away is the complicated build scripts. So, for example, I was like, cool, there's Executorch coming out, and now you can go directly from PyTorch to any platform. It sounds amazing, but then you open the project, and it just doesn't build and doesn't compile, and it's so complicated. You have to read so much documentation to figure out what are the build commands, and then it was super slow, and I had to search so long for flags that I can set do I already run the fastest? Is there another flag that I can set? So that was pushing me away so much. And then I was using burn, for example, and I was just running cargo add, and I just had it and it was fast. So I think this, for me, that helped a lot, because when you have to put so much effort into it without knowing if it runs your model at all or if it runs fast enough, it's a bit annoying.
All right, thanks everyone. Thanks, Stephan.
Thank you.